Hello friends, my name is Amit Rawal. I am professor at the Department of Textile and Fiber Engineering, Indian Institute of Technology, Delhi. Today I am going to give a series of lectures entitled Engineering Disordered Fibrous Materials via Theory of Fiber to Fiber Contacts that are designed specifically for ARPIT program. So let us go through the contents of this short course. So this course is actually divided into 4 components. The first one is introduction, where I am going to introduce the subject of fiber to fiber contacts, its relative importance, and then we are going to talk about fiber to fiber contacts in random fibrous assemblies, which is basically the calculation of number of fiber to fiber contacts, and then we are going to talk about fiber to fiber contacts in anisotropic fibrous materials, and lastly we are going to talk about the application of theory of fiber to fiber contacts. So let us start with the introduction. The textile structures or textile fabric specifically are classified in 4 different ways. The first one, in figure A, you can see a woven fabric, which is an interlacement of warp and weft yarns, and as you can see, the cream color yarns are, let us say these are warp and the pink ones are weft. Then the interlacement of warp and weft would produce a woven fabric. Similarly, we have a braided structure or braided fabric which actually intertwines the yarns diagonally. Similarly, you have a knitted fabric which is interlooping of yarns. As you can see, there is a yarn running in loop, the yellow one, and the other one is the blue one. So you can see. So again, the interlooping of yarns is actually taking place. And then the last one is a very disordered fiber network, which we call it as a non-woven fabric, which is shown here in figure D. And you can see here that the structure is oriented either in a random manner or in some sort of stochastic manner and forming a non-woven fabric by means of certain contacts. So in all these structures you can actually see the yarn to yarn contacts or fiber to fiber contacts is actually taking place. So in first figure A, you can see yarn to yarn contact is being formed here at the junction. Then similarly you have a braided fabric which is again forming a yarn to yarn contact. Similarly, in a knitted structure again yarn to yarn contact is happening, and specifically in the non-woven fabric you can see the fiber to fiber contacts as well. So different types of structures can actually give us the yarn to yarn contacts or in general fiber to fiber contacts, because yarn is actually made up of fibers. So either the fiber to fiber contacts are taking place within the yarn or between the yarns. So first 3 structures, the figure A, B and C, you can see these are actually regular structures or very ordered structures. The figure D is a non-woven fabric which is a highly disordered assembly of fibers and disordered structure. So you have different types of structures formed by means of fiber to fiber contacts. We need to understand the importance of these fiber to fiber contacts, how these fiber to fiber contacts are important for us and in what manner. So the first point which is important for us is geometrical properties, which is described for example in the form of pore size, because the pores are being formed between the fibers and the dimensions of those pores are influenced by means of fiber to fiber contacts. Similarly, you have mechanical properties, for example tensile or compression. In case of mechanical properties, the fiber to fiber contacts play a significant role because fibers are the load bearing elements and the fiber to fiber contacts are the load transferring elements. So, if there are no contacts being formed between the fibers, then the loads will not be effectively transferred from one fiber to the other fiber. Hence, you can see that there is a significant importance of fiber to fiber contacts in influencing the mechanical properties of these materials. Then we have hydraulic properties. What we mean by hydraulic properties? For example, the wetting and wicking characteristics. So, if the two fibers are not making any contacts, then apparently there is no transfer of the fluid that can actually take place between the assemblies of fibers. So, fiber to fiber contact plays an important role in influencing the hydraulic properties. The next one is electrical properties. If the material itself is electrically conductive in nature, then apparently the transfer of electron also takes place through fiber to fiber contacts. So, again it shows the importance of fiber to fiber contacts in fibrous materials. So, this list is not complete. The fiber to fiber contacts can influence the other properties which are not listed here. So, there is a significant importance of fiber to fiber contacts that characterize or that influences various properties of fibrous materials. So, as we have seen earlier that we have different kinds of fibrous materials. In case of the regular fibrous materials, it is easier to visualize the number of contacts between the yarns, but it is quite difficult to visualize and understand the topology of disordered fibrous materials. So, in this series of lectures, we are going to look at the disordered fibrous materials, and if you look at the topology of the disordered fibrous materials, then apparently the first key component is fiber orientation. That means how the fibers are being aligned within the network of fibers. And as you can see here on the right hand side, the fibers are shown like in different, they are being aligned in different directions, and the axes of these fibers are denoted by the dotted line. So, fiber orientation is a key component because it influences the different kinds of properties. For example, the pore size, which is shown here by yellow circle here, again it is highly influenced by the alignment of the fibers within the structure. It also influences the number of fiber to fiber contacts. So, the number of fiber to fiber contacts are significantly dependent how the fibers are aligned in the system. If all the fibers are aligned in one direction, then you will have minimum number of fiber to fiber contacts, but if they are being oriented randomly within the structure, then you will have maximum number of fiber to fiber contacts. Then if we look at the topology of disordered fibrous materials, then the type of fiber to fiber contact also plays a key role. As we discussed earlier, the fiber to fiber contact is playing an influential role in transferring the load, for example. Then if the contact is solid, for example, if it is a fused fiber network, then apparently you will have a better load transfer as compared to the frictional fiber to fiber contact. So, again type of fiber to fiber contact plays a significant role. Then based on above three characteristics, one can also calculate the distance between the fiber to fiber contacts that we are going to discuss in the next lecture more in detail. Then we also know that fiber volume fraction, which is the ratio of the fiber volume to the fabric volume, then it is also to certain extent influenced by fiber to fiber contacts. The next one is porosity, which is a complement of fiber volume fraction that is also defined in terms of the ratio of pore volume to the total fabric volume. So, similar to the fiber volume fraction, porosity is also a key component which is significantly important because our fibrous materials are highly porous in nature, and so porosity is also determined by fiber to fiber contacts. Then we have pore size distribution, as we have discussed earlier. You can see there is a circle of diameter d on the right hand side, and which is influenced by the number of fiber to fiber contacts, since you can see this contact and how the fibers are being aligned in the system. So, all these characteristics influence the pore size distribution. So, pore size distribution combines the effect of the porosity, the thickness of the material, and obviously the number of fiber to fiber contacts. So, next we discuss about the applications of fibrous materials. These fibrous materials have immense applications, and this shows the importance and the understanding of fiber to fiber contacts. For example, our fibrous materials are being used in biomedical side, for example in scaffolds, wound dressing applications, bandages. They are extensively used in composites, building and construction, thermal insulation, for environmental applications as air filters, as well as liquid filters, oil filters. So, there are number of applications where fibrous materials are being used, and until and unless we have a deeper understanding of fiber to fiber contacts, we will not be able to define the structure based on the application of these materials. So, the application of fibrous materials is dependent upon the structure, and the designing of the structure is strongly influenced by the fiber to fiber contacts. We need to have an understanding about the fundamental principles behind the calculation of number of fiber to fiber contacts, and the first technique which is normally used for determining the fiber to fiber contacts is stereology. And how do we define stereology? Stereology is a mathematical technique to statistically select and process the geometrical data to quantify the entities of n dimensional object through measurements of its sections and projections which have dimensions less than n. So, what it means is, if we need to determine a volume of a particular object, then we need to have cross sections of that particular object, so that we can determine the cross sectional area, and subsequently we can calculate the volume. Let me give you an example to understand the principle of stereology. If you look at the left hand side, then you will find a figure that shows an ellipsoid which is confined between the two planes, as you can see here. This ellipsoid has a height h, and it is present in three dimensional coordinate system x, y, z. Now, if we are supposed to calculate the volume of this object, then apparently you will see that we can look at the cross sectional area, and that is at a defined height dz, and if you stack these small cross sections on the top of each other, then you can actually form the complete ellipsoid. So, the complete ellipsoid is formed by stacking these small cross sectional areas on the top of each other. So, what we need to know is the cross sectional area at a particular height. So, on the right hand side you can see the volume of the object is defined in terms of the cross sectional area multiplied by height dz, and then we integrate between 0 to height, which is h. So, you can formulate a relationship between a 2-dimensional and 3-dimensional entity, or the volume of the 3-dimensional object can be calculated by means of the cross sectional area, and then you sum these areas to define the volume of the object. So, the integration actually shows the relationship between the 2-dimensional and 3-dimensional object. So, our 2-dimensional object here is the cross section, and the volume is defined in terms of cross sectional area and height. If we take the product of cross sectional area and the height, then apparently we have the volume of the object. The fundamental principle of stereology was discovered by Cavalieri, a student of Galileo, and this principle can be defined for a 2-dimensional object and also for a 3-dimensional object. So, in 2 dimensions, the principle states that the areas of 2 figures contained between the parallel lines are equal if the linear cross section parallel to and at the same distance from a given base have equal lengths. Similarly, in 3 dimensions, the principle states that the volume of 2 solids contained between parallel planes are equal if the planar cross section parallel to and at the same distance from a given plane have equal areas. So, what we mean by this is, if we have 2 objects, as you can see, there is a purple one and then there is a red one, and there are 2 planes, and the plane is defined by number 2 and the objects are defined by number 3. Then from a fixed plane, obviously the height is constant. So, from this plane 1, if the linear cross sections are same from the plane 1 along its distance, then the volume confined between these 2 planes are equal. So, this is for a 3-dimensional object, because our most of the fibrous materials are 3-dimensional in nature. So, this principle is significantly important in understanding their characteristics. So, in addition to the principle of stereology, you will see that we will be using the principles of geometrical probability. So, let us define the geometrical probability. As we know, the probability is defined in terms of the ratio of the successful outcomes to the total number of trials. So, this definition is used in conjunction with the geometrical objects, and it refers to the use of geometrical representation and calculations to determine the probabilities of outcomes. So, let me give you some examples. So, as you can see, this is a line AD on the left hand side. Then there are 2 points, arbitrary points B and C, and the distance between BC is m, and the distance between points A and D is L. So, if we are supposed to calculate the probability of hitting a point on the line BC, then it would be the ratio of m to the total length L. So, in order to calculate the geometrical probability of this 1-dimensional object, then for such calculations we need to use the geometrical probability of hitting a point on the line BC would be m by L. Similarly, if we have a 2-dimensional object, so as you can see, the square is having a circle of diameter d embedded inside, then you will see if we want to calculate the probability of hitting a point inside this circle, then we will need to use the area of this circle and the area of this square, and the probability of hitting a point on this circle would be the ratio of the area of circle to the area of the square, and then you can simply calculate the probability of hitting a point on a circle, and this is for two-dimensional object. Similarly, you have a three-dimensional object which is defined by a cylinder, as you can see here, of diameter d and height h, and let us say that there is a sphere of diameter d, small d, as you can see with the purple one is a purple sphere is a of diameter small d. If we are supposed to calculate the probability of hitting a point on this sphere, that will be the ratio of the volume of the sphere, which is obviously 4 by 3 pi d by 2 whole cube, to the volume of the cylinder, which is pi d square by 4 h. So, this is how we can calculate the geometrical probability, and we would be extensively using these principles in the next few lectures. So, now we look at the classical Buffon's needle problem, which is also useful for our fibrous materials. So, let us say there are two parallel set of lines and we would like to hit a needle on one of these lines such that the length of the needle is smaller than the distance between these two parallel lines. So, let us calculate the probability of hitting arbitrary needle on one of these lines. So, probability of hitting the needle of length L to the parallel set of lines having a fixed distance is given by, as we have seen it earlier, it would be L by d. But since the length of the needle is smaller than the distance between these two parallel lines, it is also not necessary that the needle would always lie perpendicular or parallel to the direction of the line while it is hitting. So, for a short needle, the probability of needle with chosen angle eta hitting the line is p eta is equal to L sin eta by d, because eta is the horizontal angle made between the needle and the line. So, one can easily calculate the probability of a needle with the chosen angle eta hitting the line in terms of L sin eta by d. Now, considering the isotropic orientation of a uniform random needle, since the needle can hit at any particular angle eta, the orientation averaging should be employed here, and then accordingly p eta should be equal to L by d, and then you have to integrate between 0 to pi sin of eta d eta divided by 0 to pi d eta, which will result in 2 L by pi d. So, you can see we can actually calculate the probability of a uniform random needle hitting a line in terms of the dimensions of the needle, which is the length of the needle and the distance between the parallel lines. So, one can easily calculate the probability in this case, and this is also useful for fibrous materials, because we would like to know whether a fiber would make a contact with the other fiber when the structure is random in nature. So, this is a very useful concept, we would be using it later on. Let us start making use of principles of stereology in order to compute the out of plane orientation angle of a particular fiber which is aligned in a fibrous material. So, you can see a fiber which is making an angle theta with the z axis. If we are supposed to calculate this angle theta for a particular fibrous assembly or for a particular fibrous material, it is quite cumbersome process to calculate such an angle. So, what we do? We take the projection of this particular fiber in two different planes. One you can see on the xz plane, the pink surface is represented by the xz plane. The other projection you can easily take it on the yz plane, which is shown here with the yellow color. The same fiber can be projected on the xz plane, also on the yz plane. So, let us start calculating this value of angle theta by means of angle theta x, that is the angle made on the xz plane, and then theta y, which is an angle made by the fiber on the yz plane. And let us say there are A, B, C are the dimensions of this cuboid which is formed around the fiber. So, if we start calculating the value of tan theta x, which is A by C, simple perpendicular upon base, you can see tan theta xi, I here represents the ith fiber. Similarly, you can calculate tan theta yi, which is B by C. You can see this is tan theta y, which is B by C, and just squaring and adding these two tangents would actually give you a square by c square plus b square by c square. So, tan square theta x plus tan square theta y would give you a square plus b square by c square. And if we look at the square root of a square plus b square, it is this side, which is the hypotenuse being formed on the xy plane. So, if you calculate tan theta I, then apparently you will see it is square root of a square plus b square divided by c. So, tan square theta I is equal to tan square theta xi plus tan square theta yi. So, one can easily calculate the out of plane orientation angle of the fiber with the help of the projections taken place on the different plane, on this xz plane and also on the yz plane. As we discussed earlier, the stereology is the three-dimensional interpretation of two-dimensional cross section of materials. The closest technique to make use of such principles would be X-ray microcomputed tomography analysis. In X-ray microcomputed tomography analysis, you have an X-ray source which you can see with a black dot, and there is an object which is placed on the rotation stage, and once you start rotating this object with the help of rotation stage, the image would be projected behind it, and if you start collecting all these images while the rotation is taking place, then you can actually reconstruct the three-dimensional object. So, just taking the projected image on a two-dimensional section and then recombining together, then we can make use of the basic principles of stereology and to form a three-dimensional object. In the next set of lecture, we are going to talk about the calculation of number of fiber to fiber contacts in a random fibrous assembly. Thank you very much.